Hi students, welcome to the final exam review video. So I will be working through a couple of extra practice problems to get you ready for the final exam. So the final exam will technically be cumulative, but with heavy emphasis on topics that have been covered since the midterm. And it's going to be the same format as the midterm. There will be just multiple choice questions, and there will be 20 multiple choice questions. And just like the midterm, you'll have 2 hours to do the questions. Okay, so I'm going to work through some of the extra practice problems from the website, and so I'm going to start off with the UML extra practice problems, question number 1. So we have the following UML diagram, which is for author, book, and reader relationships. So as we can see here, each author can write between 1 and 3 inclusive books, and each book can have 1 or 2 authors, and each book can have 0 to 4 readers, and each reader can have 1 to 5 books that they read. And so we're just going to work through this first question. If there are 6 authors, what is the minimum and maximum number of books? What is the maximum? What is the minimum and maximum number of readers? Okay, so we'll just bring this text over here. Okay, so we know that we have 6 authors, and so the minimum number of books in this case, I guess, happens whenever an author might write just one book, and each book might have two different authors. And so in that case, where we have 6 authors, and they write 1 book each, and each book has 2 authors. So this ends up being the minimal case, and in this case, since each book has 2 authors and each author is author on only 1 book, this gives 3 books in total, and that's the minimum. Now, for the maximal case, we could have that each of these authors writes 3 books, and that each book only has 1 author. So basically, each of the 6 authors writes 3 books with no co-authors. And that's the maximal case, and that ends up giving you 6 authors times 3 books, which is 18 books in total. All right, and now for the number of readers. So in the first case, we look at the case where we have 3 books. Okay, so each book could have 0 readers. As we can see by this 0 to 4 multiplicity here. So the min number of readers for 6 authors is 0. And the max number, so in that case, we would be dealing with all 18 books in this maximal case up here. And we could have 18 books here, and each of them could be read by the maximum of 4 people. And so that gives us 18 times 4, which equals 72 readers in that maximal case. And just thinking over this really quickly, that is with each of these readers reading only 1 book. So each reader reads only one book, each of 18 books is read by 4 people. And so that gives you the maximal case. Okay, and so that is part A. Now with part B, so if there are 6 readers, what is the minimum and maximum number of books? And what is the minimum and maximum number of authors? Okay, so we have 6 readers. And let's just figure this out really quickly. So the minimum number of books, so each reader reads between 1 and 5 books. So it could be the case that we have, and each book has up to 4 readers. So you should be able to see that we need at least 2 books here. And that is because each book can be read by only up to 4 people. So we can't have one book, we can't have one book and 4 readers, because each reader needs to read at least one book, and each book can only have up to 4 readers. So we can't have one book read by 6 people. So we need at least 2 books. And then, since books can have 0 readers, we can have any number of books over here, and it doesn't matter how many readers there are, since there don't have to be readers for every book. So we can actually have infinitely many books in the maximal case, and that's just because they don't have to have any readers. And so let's look at the author's case. So with authors, let's say we have the minimal case of 2 books. Then what we could have is just one author writing 2 books with no co-authors. And that means that we can have just one author in the min case. And then, for the same reasons that we can have infinitely many books, we can have infinitely many authors. So in the maximal case, we could have infinitely many books, and in that case, the number of authors is also unbounded, so we could have infinitely many authors. Okay, so that's the UML review. And now we will move on to some triggers. Okay, so we have these triggers social network extra problems. And so this is the same data set that we used for the social network SQL exercises, including the triggers and so forth. And so I won't describe the schema in detail. We have high schoolers, friend, and likes table, just like in the exercises. And so we'll be focusing on this question 1, which is to write triggers to maintain symmetry in friendship relationships. That is, if A and B are friends in the database, then BA should also be in the database. And so initially we know that the database obeys this constraint, and so we just write triggers that maintain this symmetry relation. So namely, it needs to satisfy cases where we insert into the friends table, and I will just start updating this. So we have to symmetry. So we have to deal with inserting into the friends table. So say inserting A, comma B. Updating the friends table. Say ID A becomes ID be in the database, and also deletion of like a tuple AB. Okay, so we can do this with non-recursive triggers, and that's what this question is asking about, to write triggers to maintain this symmetry. And so with non-recursive triggers, which again from the lectures means that triggers won't fire more triggers, we can do this with 3 different triggers, one for each of these cases, one for inserting, one for updating, and one for deleting. And so let's just go through the insertion case first. So we'll create trigger T1 for, actually we'll call this T insert. And after an insert on friend, so this is the case where we add AB to the database. So we can reference new, remember? So whenever we have the ID of the first friend that was just inserted, and they're not already friends with the second person, we can say when new.id1 is not in select ID2 from friend where ID1 equals new.id2. And so basically what this when is checking for, oh, and I guess I should also add for each row, because this is a row level trigger. So whenever we insert AB, but we don't also already have BA in the friends table, that's what this when is checking, then we want to fire this trigger. So we'll begin and end, and our statement will just be very simple. Insert into friend values ID2, ID1. So whenever we insert AB, but BA is not already in the friends table, then we insert BA. And that's what this trigger does. So that covers the insertion case. And so now let's take a look at the update case, which is where in the friends table an ID changes value. And so we'll create a trigger T update, and after update on friend for each row, okay, so there are several cases that we need to capture here. So we can actually generalize this pretty easily with non-recursive triggers. Whenever A changes to B in the database, and we want to change all of the places where A occurs in the database. And so we can do that just by updating friend and setting ID1 equal to new.id1, where ID1 is equal to old.id1. And so what this statement does is we look at each row in friends, and whenever the first student ID is equal to the new student ID, wherever we have the first student ID equal to the old first student ID, we set the first student ID to be equal to the new first student ID. And we also need to update friend and set id2 equal to new dot id1 where id2 is equal to old id1. And so that's taking the case where we change the value of we've changed the value of the second friend. So so basically the second ID is equal to the ID before we changed it, and so we have to set that second ID to be the new one. And then we have exactly symmetric cases to deal with ID2 changing. So if the first ID was equal to the old second ID, then set the first ID equal to the new second ID. And also, whenever the second ID is equal to the new second ID, is equal to the old second ID, set the second ID to be the new second ID. So, oops. So hopefully that makes sense. And then the last case that we have to deal with here is the case of deletion. So if we delete friends A and B, we also have to delete BA. So we will call this trigger tDelete, and after delete on friend, for each row, so we simply delete from friend where ID1 is equal to old ID2 and ID2 is equal to old ID1. And end. And so what that does is we delete A, B, and then just go through and delete BA. Cool. And so that is a quick review on some triggers. And so now let's look at some transactions. So we're going to be doing the transactions extra practice problem 2. So we have this table of items which have a name and a price, and two transactions T1 and T2 occurring at the same time. And so what T1 does is inserts into an item scissors with price of 40 and updates the price of pencil to be its original price plus 30, and then it commits. And T2 just selects the average price of all of the items, and then selects the average price of all of the items again. So these two statements do exactly the same thing, but depending on the state of the database, might end up being different. And so what this question asks is, what are the possible values selected as this average A1 and A2 in different isolation levels? So we go through, what is it in a serializable case, in a repeatable read case, in a read committed case, and in a read uncommitted case. And so in the case of serializable, there are only two possible orders of execution. Either we get T1 and then T2 happening, or we get T2 and then T1 happening. Since serializable means that it appears as though one transaction completes entirely before the other one can occur. And so if it appears as though T1 and then T2 occurs, then we have, okay, so initially we have pencil at price 20 and pen at price 30 in the database. And so if T1 occurs first, then we'll have three items. We'll have scissors priced 40, pencil priced 20 plus 30 because of S2, and pen priced 30. And so that average is just going to end up being the average of 40, 50, and 30, which is 40. And so in this case, T1 completes entirely, and so S3 and S4 give the same value as the result. So in that case, we get 40 and 40 as those values. And if T2 occurs first and then T1 occurs, then scissors aren't in the database at the time that these averages are computed, and the price of pencil hasn't been updated, so the price of pencil is still 20. And so in this case, again, we have the same average computed, and it's just going to be 25 for the first one and also 25 for the second one, since they have to appear to execute one right after the other before anything else executes. So that's the serializable case. And now for repeatable read. So in this case, so repeatable read, remember, means that anything read has to be committed, and also if you read something more than once, then if on the second time that you read it, the value has to be the same as the first time that you read it. And so in this case, we can still have the serial executions. So these are still possible. And let's see if anything else is possible. So, for example, we could have the case perhaps where something occurs between the computation of these two averages. So if we selected, if we got this first average and then inserted this item into the database, and then computed the second average, we wouldn't actually be able to read the value for scissors because, as we recall, in repeatable read, things have to be committed already. So that isn't possible. And so we would need to go all the way to a commit for something to be read by S4, but not by S3. So if we compute the first average and then all of T1 completes, and we get to S4, and we're selecting the average price, then we also can't do that because we've updated the price of pencil since we computed the first average, and since we have to read that value for pencil again, then this execution can't happen. We already read one value for pencil, so we have to be able to read the second one again. So it turns out that we can't put any of T1 in between S3 and S4 in this particular repeatable read case. So that means that T1 has to occur either entirely before or entirely after T2. So in this case, we get the same behavior as the serializable case. We get 40-40 and 25-25, and nothing else can happen for repeatable read. Now for read committed, so again, we can get the serializable case, but we can also get some other stuff here. So it is it's possible that it's possible in this case, since we only have to read committed values, that that we could compute the first average, and then we would only be reading committed values from the first one, since T1 hasn't committed yet. And so in that case, we have S3 happens, and then all of T1 could happen and commit, and then S4 could happen. And both S3 would read only committed values because none of T1 has happened yet, and then S4 would read only committed values because T1 has committed. And so that is possible, and in that case we would get 25 for the first average, since scissors hasn't been inserted yet and the price of pencil hasn't been updated, but we would get 40 for the second average, because in that case we do have scissors at price 40 and pencil has been updated to price 50. And so for read committed, we also get an additional possible final result. And now if we have read uncommitted, well, in this case, there's no guarantee on the order that we read things at all. We could T2 could read any interleaving of possible executions, and so in this case we would have everything from above. So we would have 40 40, 25 25, and 25 40 again, but we would also have some other stuff. So in this case we could start with S3 first, which would give us 25 for the first value, and then we could have S1 execute, in which case we would have scissors in there, and then S4 could happen, and in that case we would have the average of pencil at 20, pen at 30, and scissors at 40, which is an average of 30. So we could get that execution. We could also get S1 happening, and then S3, S4 happening. And in that case, we would get the database with scissors in it, but without the price of pencil updated. And so in that case, we get 30 for the first average and 30 for the second average. And we could also have the case where we have S1, and then S3, and then S2, and then S4 happen, in which case we would read 30 for the first average and 40 for the second average, because we would have, for the second average, the price of pencil has also been updated. And so those are all of the possible interleavings that can happen. We could end up with 6 different possible executions when we read uncommitted, compared to only 2 when we do serializable isolation level. And so that's a review of the different types of isolation levels that transactions can have, and an idea of their behavior for each. And so one thing, so in this case we did have serializable and repeatable read behaving the same, but remember that in general that isn't the case, because in repeatable read, you can still have phantom tuples happen. So if we hadn't had this second update command in transaction 1, and it had just been inserting scissors into the database, then that phantom tuple could have caused a different execution. So in that case, we could have computed the first average, and then scissors could have been inserted, and then we could have computed the second average. And that doesn't violate anything with repeatable read, because we're still only reading the value of scissors once. So that's the one thing to remember that makes repeatable read not as good as serializable, is that phantom tuples can happen. And so that's it for now with transactions, and now I'll move on and do a quick recursion problem. So in this case, we have a database with nodes which have a node ID and an edge with 2 nodes and a weight between them. And so this just represents a graph where we have points, which are nodes, and edges between them, and an edge consists just of 2 points. And so this this first question just asks you to find all node pairs n1 and n2 such that both of the nodes are read and there is a path of length 1 or more from node 1 to node 2, and then to finally sort the result by n1 then n2. And so just recall we have this schema: node with a node ID and a color, and edge with n1, n2, and a weight. And so back to this query, find all node pairs that are both read and there's a path of length 1 or more between them. Okay, and so we can do this pretty easily with recursion, and so we'll just imagine for now that there is a path which has just a path relation with n1 and n2, which just specifies that a path exists between nodes n1 and n2. And so we will do a quick recursive query to compute path, and then finally we will use path to get nodes with a path between them that are both read and sort by n1 and then n2. And so our final query is easy. If we have this relation path, then we can just select star from path where n1 is read, so n1 is in select NID from node where color is equal to red, and n2 is in the same thing. And so then we have nodes that have a path between them and are both read. And then the final requirement was to sort by n1 and then n2. So order by n1 and then n2. And so that's a pretty easy query, and the real question here is to compute path in the first place. And so we use the with recursive syntax, and so we declare path up here. As, and then we do our recursive subquery. And as a base case, we know that anything in edge will also be a path. There'll just be a path of length 1. So we'll use as our recursive base case, select n1, n2 from edge. And then we build this up just like in the recursion demo video. We union that with, so what do we need to have a path? What we can do is look at all of the edges and at all of the paths that already exist, and we know that there's a path between n1 and n3 if n2, n3 is in edge. And so to formalize that, we can just select path n1, edge n2 from path and edge, where path n2 is equal to edge n1. Right? And so what that does is goes through and finds all of the existing paths where the second node in the path is equal to the first node in the edge, and adds the first node of the path and the second node of the edge to path. And so it just goes through and builds up the paths one edge at a time, and ultimately the system will not have anything new to add to this, and it will know to stop, and then we will have all of the paths in the graph. And so our final recursive query here is to compute all of these paths and then select all of the paths such that both the beginning and ending node are red. And so that solves that question. And now we will move on and do just one OLAP problem. Alright, so in this case we have a data set, student, which has a student ID, name and major, instructor with an instructor ID and a department, and classes with a class ID, the university it's taught at, and the region it's taught in, and the country it's taught at. So for example, we would have like Stanford, West, and United States. And then took has student ID, instructor ID, class ID, and score. And so that is the score that the student got in the class. And so you see that this is a star schema. If you remember the OLAP videos, where took is the central part, and all of these other three tables will natural join to took, so that you can get information on who took what class, and get information about the student and information about the instructor. And so anyway, we will be doing just question 6 here, which is use with rollup on attributes of the class table to get average scores for all geographical granularities by country, region, and university, as well as the overall average. And so this is pretty good. So I'm just going to copy this question over. And also copy the schema. All right, and so we can work with this. And so what we want to do is create an OLAP table. We'll call it table T. And then what we want to do is compute average scores for all geographical granularities. So what we're really interested in is the join of took and class, since it's class that has the university, region, and country. And so what we can do is create a new table, T, and select country, region, university, and we wanted the average scores for all of these geographical granularities, so we'll do average score as S, and we want this from, as we said before, took join class, since we need score and we need all of these geographical granularities. And so what this ends up being is took natural joined with class, and we want to group by country, region, and university, and it said to use with rollup. Okay, great. And so this creates our table, and then I argue that now to get the average scores for all of these geographical granularities, we can simply select star from T. And the reason that this works is because we have rollup. We're going to have a table with country, region, university, and S, which is average score. And we're going to have some tuples that look like this: value, 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 average, where we have the country, region, and university. And so what that is just the average score at that university, which is the first geographical granularity that we're interested in. And we'll also have tuples that look like this: value, value, null, average. And so what that is the average score across all countries with this region. So the university value being null means that it's aggregated across all universities in that region. And so that will get us the region granularity. And then we'll also have tuples that look like value, null, null, average. And this is the average across all universities and regions within a country. And so that's our third geographical granularity. And we will also have null, 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 average, which is just the average across the entire database. And so those are the only types of tuples that rollup will give us. If you recall, rollup always nulls out things from the right over, but it's impossible to have something like null, value, value, average. because this works only with cube. And rollup gives us, in this case, exactly what we want. And so we just create this table with rollup, and then we select star from it, and then we're done. We get averages at each geographical granularity. And so hopefully that gives a little bit of clarification on what OLAP queries do. And so, yeah, that's it for my video today. I wish you all the best of luck on the final. I hope that this demo was helpful to review some of the concepts. And just thank you very much for the opportunity to run these office hours this quarter. It's been a great pleasure for me, and it's been a great pleasure for both Professor Whittam and for me to run this class and to deliver such great content to the entire world. So thank you for paying attention. Again, best of luck on the final, and I hope that you've found learning about databases to be useful, and I hope that you all use databases in your jobs in real life, and that you always come back to this class and remember it as a great experience. So thank you very much, and good luck on the final.